In this video, we're going to look at the concept of statics, also known as static equilibrium. It really applies Newton's first law for both translation and rotation in order to get to this point. So when we talk about static equilibrium, an object at rest remains at rest. And there's two conditions. The first one is that the net force is zero, right? And of course, that the initial velocity is zero. But this isn't actually enough because, and it would have been enough prior to the idea of torque. The reason for that is that we also need to be able to say that the net torque is zero, right? Because if you apply a force on the left and the right, yeah, the net force is zero, but that will cause it to start to spin. And so what we actually would need is something like this. Maybe half the forces there and there, or like the first picture, the forces are both applied right at the middle. So you just there's more to consider. Now, statics is a really big deal. It's an entire sort of field of study. And right, if you're studying engineering, it's probably one of the first, engineering courses that you will take in full. That's a kind of technical. But some things really do need to stay at rest, right? You don't want to build a bridge, a dam, a skyscraper, and have everything start to move. So here's an example, right? If we build basically the simplest bridge you can, you have a plank, a piece of wood, and then there's two, supports, one on each end. And you think of a person standing in the middle of the plank. So force one and force two are the upward forces that holds the bridge in place. How big are they, right? Are they equal? How much of the forces on each end? If there's a person, pushing down with a normal force, and then there's the weight of the plank itself. So there's a couple things to do. Net force in the y direction, F1 and F2 together add up to Fn and Fg. That's pretty straightforward. That's something we've done before. But it doesn't tell us how big F1 and F2, only that together they have to balance out. It's symmetric, and the person is standing in the middle, so it makes sense that would be they would each be half of the force. But if the person moves, it's no longer as obvious what will happen. Maybe it's obvious to you that F1 should grow, but by how much? And so in order to do that, we add in the net torque equals zero equation. And net torque equals zero will allow us to figure this out. Whenever we're doing net torques, we always have to pick a pivot point, right? So let's think about this one, right? Here's a girl standing a third of the way along the plank bridge, and we want to find F1 and F2. So our free body diagram is no longer just a dot. We're calling these extended body free body diagrams or extended free body diagrams, because once we're dealing with torque, it's really important that we know about where the force is acting relative to a pivot point. We're going to apply the first law, both net force and net torque. F1 plus F2 equals Fn plus Fg. But in order to apply the net torque equals zero, we have to pick a pivot point. There's maybe four that you could do. You could pick either of the ends, one of those two. You could pick where the girl's standing, and you could pick the center of the board. Those are sort of the four obvious ones. You can actually pick anything. But it turns out you usually want to pick one that is a pivot point at one of your unknowns. So it simplifies our equations. The only things that are unknown here are F1 and F2. So I can pick a pivot point at, say, F1 on the left, which also makes sense since we tend to, put the origin on the left and, positive is out to the right. So that kind of fits with our Cartesian coordinate system. So the net torque equation then becomes this: F2 at a distance of L minus Fn at a distance of L over 3 minus Fg at a distance of L over 2. Now, why is the force 2 providing a positive torque and Fn and Fg providing negative torques? Well, that's our convention, that a torque that would cause something to move counterclockwise would be your thumb pointing out at you, and that would be a positive torque. And things that could cause it to go clockwise rather would be negative torques. Then we can solve for F2. The L's all cancel out, and you end up with 267 newtons in this case. Now, that was the power of picking a pivot point where a torque was not going to, or a force was not going to apply a torque. By doing that, we're able to solve for one of them, and then we can go back and just use our net force in the y direction equals 0 equation to say F1 plus F2 have to equal 700 newtons. We know what F2 is, so we can find F1, right? Here's another example. This one is no longer just a plank. Well, it is a plank, right, that has a weight of 100 newtons, but it is attached to the wall with a hinge, and then a string is attached out at the end. Now we have a force at an angle. So the questions we might want to answer are, what is the tension in the cable, and what force does the hinge exert? So how do we do that? Well, as always, net torque and net force have to equal 0. Since the beam is at rest, and the net torque around the hinge, which is what I'm going to call my pivot point, should be 0. This is actually pretty straightforward. There are only 2 torques if we ignore, or if we pivot around the hinge. Force of tension times L sine of 45, because the distance L is the length of the board. The angle there is sine of 45, minus, because the force of gravity will pull it in a clockwise direction, so a negative torque, FG L over 2, because gravity always pulls at the center of mass, sine 90. You can simplify that, and you end up with FG over 2 sine 45 equals force of tension, 100 newtons divided by 2 sine 45 gives us 71 newtons. There's still something else to figure out. What force is exerted by the hinge? And for this one, I'm actually going to think of it in terms of x and y coordinates here. We know that the tension has a y and an x, and we know that the net force in the x has to be equal 0. So Ftx and Fty are both 50 newtons. And in the x direction, right, the horizontal component of the force from the hinge, I'm just going to call it H here to avoid lots of subscripts, has to be equal to the force of tension. So it's 50 newtons to the right. In the other side, or the other component, the force in the y direction has to be that. And so we've got a vertical force upward and a downward force of gravity, right? So we've got 50 newtons up. And 50 and 100 newtons down, so we need an additional 50 newtons up. So that hinge is also applying a vertical component force. Now, you could combine them together to figure out what that is if you wanted to find the angle at which they are acting. But since they're both the same, it's a 45-degree angle. So what could we have known about the horizontal and vertical forces without even calculations? Well, if you think about the torques around a different point, say the center of mass, now the force of gravity doesn't matter. But if you apply that force of tension and you think of the center as a pivot point, what would happen to the other end? Well, it would rotate in a counterclockwise direction down, and it would rotate down. So you know there has to be an upward force, the horizontal. You also know, just from Newton's first law in the x direction, that if it's being pushed into the wall by the tension, that the pivot or the hinge has to push outward. So how do we solve a statics problem? First, you draw a free body diagram, and we use sort of the outline method. We think of the outside of the object, and we put all the forces on where they are acting. Then you sketch the directions of all the forces as much as you know. Sometimes you may not know because of the net torque equation. You might have to go back and fix it. Apply Newton's laws, net force equals 0, net torque equals 0. The force law that is easiest to solve, but you need both equations. There's usually one of them that's simple, and then the other one is more complicated, but you are always going to need both equations. Sum the torques for any pivot point or multiple pivot points. You can actually do this. You don't have to limit yourself to just 2 equations where you've got the net force and then 1 torque equation. You can actually do as many torque equations as you like around different pivot points. That's the beauty of statics and static equilibrium, that around any pivot point, they sum to 0. But always pick the smart one, if you can, that eliminates an unknown. Be flexible. Don't be, rigid or static. Anyway, so here's our last big example. This is the leaning ladder. So if you lean a ladder up against a building, right, it's not fastened to the building. It's not fastened to the ground. And if we imagine that the wall is frictionless, which is not a terrible example compared to the grip on the ground, you put a 70-kilogram person halfway up a 10-kilogram ladder. The ladder is set as a 60-degree angle, and the wall is frictionless. So there's the pieces of it. No friction there, 70 kilograms, 10 kilograms for the ladder, and a 60-degree angle. You may want to draw this out to help you think about what's the outline of the ladder. Well, the ladder itself, is just a board, basically. And we want to draw and label a force vector, no magnitudes on there. Add another force, repeat until all the forces are drawn. So, I would probably start with the weight of the ladder, pulling straight down on its middle, then probably the weight of the man. Then I would think, well, the wall is providing a normal force and the ground is providing a normal force. And probably the ground is also providing a frictional force, because we are told that the wall is frictionless, but the ground isn't. So this is what I would draw. I may or may not be right about the direction of the static frictional force, but if you think of what would happen to the ladder if the ground had no friction, you think about it sliding out from under you. So probably the frictional force is toward the wall. So we can go a little bit further. We know that the normal force that the man is providing is equal to his weight. So that's a 700 Newton force because everything's at rest. And then the weight of the ladder is 100 Newtons. So those are both pulling straight down, happen to be at the center of the ladder. The net force in the y direction tells us that the floor is providing an upward normal force of 800 newtons because there are only 3 forces in the y direction. The net torque tells us then, if we pick the pivot point to be the floor, that the wall must be providing 230 newtons. I'm not showing all the math here, but that's basically saying that the force of gravity and the normal force from the man are providing a clockwise torque, and the wall is providing a counterclockwise torque. So we're almost done. The next force, the last force, is the force of static friction. In order for this to be at static equilibrium, it must be providing an equal force to the right that the wall is providing to the left. So it's at equilibrium. All right. So what is our big idea here? Well, the static equilibrium is a special case of Newton's first law, where both the net force and the net torque are 0. There's no translating. There's no rotating. You pick a pivot point and you sum torques. And we use this multiple times, multiple equations, to allow us to solve for many unknowns.